Okay, here's the first one. Now, it seems like there's a few students that are getting overwhelmed with the different types of standard deviation and things like that. Just try to take each question just one at a time. So, um, here we are, this question. Recall that there are four suits: spades, hearts, clubs, and diamonds. Standard deck of playing cards. Suppose you play a game in which you draw a card, record the suit, replace it, shuffle, and repeat. You have observed 10 cards. Define X equals the number of hearts observed. Okay, here we go. Well, show that it's a binomial random variable. I think we are doing pretty well on this because we check the bins. Is it binary? Okay, you either get a heart or you don't get a heart, and that's how you would describe that. So you would write this down. Are they independent? So when you draw a heart, it doesn't affect the next card that you draw because you're putting the card back in the deck. The number is set. We're going to do this 10 times, 10 trials, and the probability is the same. 1/4 of the deck are hearts. Okay, find the probability of observing fewer than 4 hearts in this game. Fewer than 4 hearts. So that means either 0, 1, 2, or 3 hearts. So in other words, you draw 10 cards and only 2 out of the 10 are hearts. Okay, how do you do this? Well, let's see. We could do 10. Here we go. 10 cards. None of them are hearts. There's a 1/4 chance that we get a heart, and we get no hearts. And there's a 3/4 chance that we get other cards, and we get that all 10 times. Plus, the next one would be, let's do 1 heart. 10 cards, only one of them is a heart. You have a 1/4 chance of drawing a heart. You got that one time. 3/4 chance, not a heart, and you got that 9 times. Plus, and we're going to go 10, we got 2 hearts, and we're going to add all those together. 2 and then 3. So this process, 1 time, 2 time, now for 2 hearts, and for 3 hearts, and then add them all together. But since it says observing fewer than 4 hearts, so 3 or less, you can go to binomial CDF, right? And you're going to do 3 or less. Okay. So binomial CDF, 10 trials, right? 10 trials. I have the worst pen right now. 10 trials. Let's see, what's the probability? 0.25 for the probability, and our X value is going to be 3. Okay, there you go, that's the first one. Okay, let's look at this one. What do we got? Suppose 72% of students in the U.S. give their teacher a positive rating. A survey was conducted in which 500 students were randomly selected. Okay, let X be the number of students in the sample who would give their teacher a positive rating. Now, there's really not much to work with here. So, let's just start. Letter A. Is it approximately a binomial random variable? Well, binomial. They either give the teacher a positive rating or they don't. It's kind of a yes or no survey question. At least it should be. Independent. Each student's opinion is not going to be affected by another student's opinion. The number is set at 500, and the probability is going to be the same, 72%. So, and we're okay with the sample size because this is in the entire U.S. So we're assuming that there's more than 5,000 students in the U.S., so we're safe there. Okay, letter B. Use a normal approximation to find the probability that 400 students or more would give their teacher a positive rating. Oh, normal approximation. Normal approximation indicates that it's going to be a z-score. Okay, now first of all, can we do the normal approximation? Well, 0.72 times 500 and also 0.28 times 500. Are they both bigger than 10? 10 plus? Yes, they're both bigger than 10 if you do that. So that means that we can use the normal approximation. So that's the way our data would look like. Okay, now we need, well, we don't really, like I said, we don't have a lot to work with, so it is going to be, here's our average, our expected outcome. So the number of students, 500, times the probability, which is 500 times 0.72, and what do we get? So that equals 360. That's what we should expect to get, given that we have this probability of 72 and ask 500 students, 360 would give a positive response. How about the standard deviation? Well, we do this. I'm not going to write down the formula, I'm going to run out of room. It's the square root of the number times the probability times, what is it? 1 minus the probability. So, what is that? Oh, that's not 78. That's 72. I got ahead of myself. And that's 28. Okay. So, what's that? So here we have the standard deviation of 10. So we're going to have a z-score. See, when we see this normal approximation, that's kind of a tip-off that we're going to use a z-score. So the z-score is, let's see, the number that we're interested in, which is 400 or more, minus the average, we should expect 360, divided by 10. That's going to be 400 minus 360 is 40 divided by, so that's going to be 4. Wow, that's way up there. So let's see, probability of 400 or more students. So it's going to be normal CDF of negative 1,000 to 4, and we're going to subtract that from 1. It's going to be a super small number. So yes, very, very, very small chance of that happening. Okay, so given that we expect 360, we get 40 more than that, given the sample, with a very tight standard deviation, almost no chance of that happening. Okay, there's that. Okay, 20% of Super Crunch cereal boxes contain a secret decoder ring. Let X equal the number of boxes of Super Crunch that must be opened until you find a ring. So that sounds like a geometric for sure. So keep opening them until you get that ring. How do you show that it's a geometric? It's binomial. You either get a ring or you don't get a ring. If you don't get a ring, open another box. Independent. Each box is independent of the other box. The fact that that ring is not in that box has no effect on any other box having a ring or not. Okay, now, and we are just going to keep opening boxes until we get a success. Okay, just one success, and then we're going to stop. So that's the number part, and the S. which is the same probability, and they say that 20% for all of them. So there we go. We have established that is a geometric random variable. Find the probability that you have to open 7 boxes to find a ring. Well, if you open 7 boxes, it means that the first 6 didn't have a ring. So let's see. 20%, right, that you get a ring. And how many times did you get a ring? Once. You keep opening boxes until you find it. And then 80%, how many times did you have to open boxes and not get a ring? Well, 6. 6 times you didn't get a ring, and on the 7th one you got a ring. There you go. That's how you do that. And the probability is, what is it? It's 0.052. 0.052. So you get about a 5% chance that you would have to open 7 boxes before you found the ring in this situation. Okay, the next one says find the probability that it will take fewer than 4 boxes to find the ring, which means 3 or 2 or 1. Now we could do all of those and add them together, or do geometric. Is it PDF or CDF? It is CDF. Okay, fewer than 4 boxes. So it's that CDF for 3. Okay, and what's our probability? 0.2. Okay, so there's that one. And the answer should be 0.488. Okay, now, how many boxes would you expect to have to open to find a ring? Well, let's see. 20%, 20 over, I'll write this down. So it's 20 over 100%, right? It's 1/5, right? There's a 1/5 chance that you're going to open a box and get a ring, which means if it's 1 out of 5 times, you would expect that you win 1 out of 5 times, meaning you would have to open 5 boxes. Or at least that's what you would expect. You would expect that you would win once out of 5 times, 5 boxes. There is that.